Hello and welcome back to the tutorial series where we make a simple platformer for Overlap2D using Overlap2D runtime. In this third series we're going to make a physics kind of thing and collision detection and some raycasting to make our physics object not fall away from things. So let me just, I made some changes from the previous version. Let me just run this. So this is what we have currently. As you can see, I just put some pillar here, put our ship a bit up so it can fall and one can see it falling. And then I removed the little if statement that was stopping it from falling to the ground, so now it just falls down, because we're going to do it properly this time. Besides that, I kind of centered the camera exactly on the ship. Before that we were using player get X only. Now I'm just incrementing that by player get width divided by 2, so it's in the center of the player. And I just added the dimension component here in the player class. That is, the dimension component is a component that has just two properties in it. It just width and height. It also knows its bounding box and polygon if it has any, but right now it's just width and height for our ship because just a sprite animation. And so yeah, the get width is returning dimensions width, and that's it. Obviously we should have get height, but I'm too lazy for that. So what we're going to do next is make the ship stop on the ground. Now because we already kind of done that before, when the overlap was young and we had this previous runtime, we had an older version of this platformer, and it had this little bit of code done for raycasting, so I'm just going to reuse that in our example. Well, first of all, here we need to make a method that will do the raycasting, but before we get there, let me just explain the theory here. Now we want this ship to go down because of the gravity, move down, and then stop right here because this thing should stop it, right? And then, now the way it's done is we do a thing called raycasting. So we cast a ray is basically a kind of a line. It's a segment that has start and that has an end. And so if you imagine a line that starts from the middle of the ship where my mouse is and then goes somewhere here under the ship, so this is kind of a ray, right? And so what we want to do is see if this imaginary line here, if it's crossing any of the box2D polygons, box2D objects. So if it is kind of intersecting any polygon, then our ship is touching something, and so it should stop, it should not fall anymore. So that's the logic behind it. Now you may ask, why don't you just make an imaginary line and use libGDX awesome intersection utilities that can intersect any line segment with a polygon? That's an option as well, and you can do that, but the reason we're using box2D raycasting is because it's done using the box2D engine, and it's really fast. It's really fast because it's going to use native C++ code. It's not going to be a simultaneous action. It's not going to be a synchronous code, but it's going to be asynchronous. So you might do a raycasting, and then just a little bit time later you will have an answer to that raycasting if it intersects anything or not. So that's what we're going to do now. First, in our act method, our player, let's call a method that's called raycast. And well, let's create that method. Right now it does nothing, and we're going to start copy pasting from here. Now these are some calculations I made here just so we can decide on the size of the ray. Now here we need a ray gap, so the location where the ray is located, we want it to be in the center of the item vertically, right? So it has to be in the dimension component height divided by 2. Now the next thing here is ray size. What's going to be the size of the ray? You can generally have it of the fixed size, but that's not good because sometimes the delta time is different and the ship moves at different speeds. So what can happen here is if your computer lags or something like that, so at one iteration it might be here, and on the next iteration it will be already here. So imagine it's here and then it's here, so we cast ray here, it doesn't touch anything, then on the next iteration it will already pass the wall, and we cast ray and again nothing happens, so it will just pass through, right? So if we don't have much frames per second here, it will go right through. That's why we want to base our ray based on the size of the delta, so based on the size on the time of iteration. So if we know that we know our speed and we know the current delta, we can calculate where the ship is going to be next time and make sure that our ray is not smaller than that. So that's what we're going to do. We're going to take our vertical speed and multiply that by delta. I'm really not sure why this happened. Like at the end we can try to remove this additional multiplication or not, because why do we plus that? Alright, we'll figure that out later. So that's our speed and that's our, and we multiplied by delta, but I'm not sure why this is here, and we'll test later. So now we have the ray size, and just to make sure our ray isn't very small, we're just going to have this little check here, just make sure it's not too small. I'm not sure I like this check because it depends on the world size, so let's just skip that one as well. And then we go forward, and obviously we want to check for collisions only where we're moving down. If we're moving up, we don't want any collisions happening right now. And so we're gonna do this. And let's create our vectors that describe the ray that we're going to be casting. So something like that. Let's see. So this is the ray from. We wanted to start from the x position of the item, which is transform component x, and plus the width divided by 2. So this is dimensions width. This is obviously the center of the item. And then we need to scale this to our world, to our physics units, because the physics sizes and the world units are not the same. The reason is you can't, there are certain values that you want your physics world to be in the range in. You don't want like big values for physics world coordinates. So that's why we have this little scaling. So in case your world is kind of big, then your physics world won't be that big. So yeah, something like that. I know it's a bit complicated. So yeah, there's just a number you have to multiply this thing with. Let's copy paste that. Okay, 1, 2, 3. Okay, and then let's copy paste this here, and this has to be y. This has to be y, and then the width. Now, just to quickly understand this, we're taking the center and we're taking the other center. So it starts at the center, and then we're taking the same x, but we're taking the lower y. So we're taking the y minus ray size. So we our ray starts from the bottom of the ship plus the ray size, right? So this is ray from, and this is ray to. Now that we have our ray information here, let's do the actual raycasting. I'm going to copy paste that here. So we need the world, and unfortunately our player have no idea about the world at this point. So why don't we go ahead and pass it to our player. So SimLoader has the world. Now player would be, oh, we don't have a constructor, so we have to create it here, like so. It will be taking world, it will be doing something like this, and we will be remembering the world. So private world. Right. So now that is done, we can go here and change this by world to world. Let's add this. add the fixture. So yeah, basically when you do the raycasting on the world, it takes two parameters, ray from and ray to, which are our vectors, and we have them. And then you create kind of a callback function, which is just a overriding method for raycast callback. Whenever a collision happens, you will get here, right? So what we want to do when this happens, first of all, we want to stop our player from falling, obviously. So speed goes to 0. Then we want to position it to the exact location we want it to be. So as you can see, we have a point Y here. The point Y here is location, basically a location where the collision happened, right? If you go here, so the point of initial intersection, right, created by Mario. Alright, so and we're going to set our position, so we're going to do transform component Y equals to this and just a little bit up. That's what we want to do. Now again, this has to be a small number. If we don't do that, it will appear exactly on the intersection point, and that's not what we want. We want it to go just a little bit up, right? But not that it will be visible or matter. Now we don't need this yet, and this is all we have to do at this moment. So now at this moment, if we run this, let's see if we have any errors here. So clear, right, I'm sorry. Now it's good. Okay, so nothing happens because there is no physics bodies in our world. While we do the raycasting, it never actually reports a collision. Now let's go to our Overlap2D editor and make sure that this long ground, actually you can see that from the previous tutorial I made it longer, so let's make sure it's a physics object. For that we need to add those both components. It has to have a polygon component, and we're going to make a default shape for it, which is, as you can see with the yellow, it's a rectangle of its size. You can of course modify it, and we'll try that later. And the next thing is, let's add a physics component, and let's just leave it to default because that's a static body and allow to sleep, and this is all we want, and we don't care about the rest. So this thing is now a physics object that just stays where it stays. Control E to export, and let us just run this thing and see what happens. Okay, good, it just stopped on that, and we can now move left and right, and this is what happens. It kind of moves weirdly. I think it's the 0-1 thing. It's just too much for this world, maybe something like that. Yeah, that looks a lot better. So yeah, we can go left and right, and it doesn't fall through, which is nice. We can again jump, and this is what happens. I have this weird lag here. Not sure why it happens. I think some kind of mistake here. Oops. But we'll figure it out later. So yeah, at this moment we have a simple kind of collision detection here, and let's check here. Okay, so let's see if this was actually important. Let's know that. I'm still not sure about the point of this one, so we'll figure it out later. Okay, so here's what we're gonna do next. Let's try, and now those things are not physics objects, so we just pass through them, right? But we can make them a physics object, so let's see if that works. I'm going to delete those guys. I'm going to click on this one and do the same that we did for the ground, so add both physics and polygon components, copy and paste here, here, and here, and then we're going to try that. 1, 2, 3, 4, 5. Awesome. Now you can even do this, I think, yes, because we'd only record collisions on our way down. Yay. So now that that works, The next step would be obviously to make our collisions not only in the direction down, but also all the other directions. Like for example, if we want the ship to collide with this pillar, we want to make race to the right when it goes right, make race to the left when it goes left, always make race to the down when it's not jumping. So in that way we would be able to kind of simulate all the walls logic here. Now today we're not going to do the left and right thing, and we're just going to stop on the simple raycasting to not fall through the objects. But before we go any further today, I want us to try something else. If we have time. So I want to implement something like a moving platform, because why not, right? Moving platforms are cool. And let it be this one. So yeah, what we're going to do is to, as you know, we have tags, so I suggest we just mark it as platform. Okay, so now that it has a name and it's a platform, we can create a system for it and attach a component to it. And just for fun, let's just copy it here as well. Let's have two platforms, right? Okay. So yeah, now in order to make the actual platform logic, we need both component and a system. So let's get to it. First of all, let's create the component. So we're going to do a platform component, and it extends component. We're kind of using the old Ashley. The new Ashley, I think the component is an interface, so it shouldn't be much problem for you guys to change later, because the component is just nothing. So what do we want our platform to remember here is its original position, because we want our moving platforms to go up and down. We want them to remember their actual position so that they can later kind of move around that original position. So we're going to do something like vector2 original position, something like that. And okay, that'll do for now. Probably add some other thing a bit later. And then we're going to create a platform system. Platform system won't work just for one platform, it will be called for all the platforms. So it manages the entire platform infrastructure. So if we have like 100 platforms, the system would be called for every single one of them. So we create a platform system, and it should extend an iterating system. Iterating system, yes, because it's going to be iterating over the entities. Now let's implement the process entity method and create the constructor. Now as you can see, it takes the family. We're going to talk about it a bit later. Now let's get back here, and what we want to do is to SimLoader has this awesome method that's called add components by tag name. So to everything that is platform, we want to add a component that is platform component. That's all. And the other thing we want to do is to take the engine, get engine, and to add the system that is the platform system. I don't think it works like that. It just, okay, it takes the system itself. So just new platform system. Okay. So now back to the family. So the system isn't going, we don't want our system to be called for every entity that is there. We want for our system to be called only for the entities that are platforms, so that has the platform component on them. And Ashley has this thing so that we can actually let our system know that it should only be called for the entities that has this particular component. To do that, we're going to say family all platform component class get, and that'll guess our family of that particular component. Now Now if we run this, nothing going to happen again. So our platform stays in this place. Now it's time to make the actual logic. The first thing I want to do for our system is to see if so we're going to retrieve the platform component, right? So for that we need a mapper, so-called mapper. So we say private component mapper. Why are we doing the mapper? We want to retrieve the platform component, but why won't we use the component retriever as we did earlier? Because the component retriever is kind of a tool created by our runtime that retrieves only the standard runtime components. Now, because this is a custom component, we have to create our own way of retrieval of that. So we're going to create a component mapper that is platform component. So it's like platform component mapper equals like this. Oops. So it should be something like that, right? No? Right, so get for platform component. Oh, this is good. So here we're just going to retrieve our current component for the current entity. So we're going to say platform component equals get entity, and this is the fastest way to get the component for an entity. So we do have our component. Let's check if the original position is null. So if it's null, then this is the very first time we're iterating this entity. So how about we remember the original position at this point? Before we go there, let's get the transform component. We're totally going to use that. So transform component equals component retriever get entity and then transform component. Right, we have that. So if this is the case, then platform component original position equals new vector to x and y. Awesome. So every time an entity enters to the system first time, we're going to create the original position and then work from there. And now the movement of this thing is going to be based on the delta time and the entire time passed, and it's going to use like cosine type of movement. So the second thing we want to do is because we want our platforms to move on different speeds, and I'm sorry, not the different speeds, but have the different offsets so they don't all move simultaneously. In our component, we can remember something like time passed, which is 0. And we're going to have initial time passed for every component a bit different, so something like math tills random 0 to, I don't know, 1 like 10,000, like this is let's make it float. So we're going to operate on the delta scale, and delta is second. Okay, where are you? Alright, so it's something like 1 to, I don't know, 2 seconds offsetting for each platform. Now we want to kind of set the position of our platform. So what we do on each iteration is we're going to do platform component time passed plus delta. So that's 1 plus equals. Yep. And the other thing is to position it according to the current delta. Now to do that, we're going to do something like transform component y equals platform component original position y plus something like math utils cosine and some kind of angle, and this number will be between -1 and +1. And we want the, like, let's say we want our the size of movement to be something like 100 world units. We'll modify that later. And here we're just going to have numbers, like does it take in the radians? It's radians, so we're going to take something like Matthew Hills degrees radians, degrees to radians, and as degrees we're just going to use time passed, right? So platform component time passed. Now time passed might be a very small number, so we want to kind of multiply that by something. Now remember, whatever you multiply this little part with will be responsible for the speed of movement, and whatever you multiply this with will be responsible for the size of movement. Now having this in mind, let's just try and run that. Let's see if anything happens to this platform. I don't think anything happens to it. Right, so the reason this wasn't working is because our platform has a physics component on it, and the physics system is on each iteration to adjust the position right back where it was, so it adjusted to the body. That means our mistake is that we can't actually move the transform component of our platform, because we have to actually work with the body of our platform, and the transform component position will actually follow. So that's what we're going to do right now. So first of all, let's take the physics body component from our entity, equals component retriever get entity. Now do we still need the transform component? It's just used. Yes, we do. Okay, so that's fine. So yeah, instead of doing that, we have to do something like body set transform, and it's going to take a vector as a position. So a vector, and I don't like this because this is going to be slow. Creating a new vector on each iteration. We're going to deal with that later. And then we say something like physics body component body get angle as an angle, and the position is going to be, of course, body component body get position X, but the Y is going to be a lot different. It's going to be plus this. Now the important thing to remember here is, because we're working the our original position, and whatever this is in world units, I want to transform that to physics world units. So I'm going to take this entire thing and multiply this by physics body loader get scale. Alright, I had to just modify this a little bit to make this a bit cleaner code. So yeah, we have this new position here, and we just calculate the new position and pass it to set transform as we were doing, and we just multiply by the scale. So yeah, if we run this now and check our platform, like you can see it like get somehow very to the bottom. So 100 was too much, and it's kind of moving slow. So I think we should change 100 to 20 or something, and also multiply this by, let's say 20, so to make it 20 times faster. Let's see where it goes. And okay, so now it goes with this speed, and you see it goes up. So I think we can do 40 here, and let's see that. That's a nice speed, and we can jump on it, and our ship will kind of move with it. And our other platform works as well. And no matter how many platforms we have, it'll work. Okay, I guess that's enough for our today's tutorial, and you guys can take a look at the codes on the GitHub. I'm going to be pushing this to the GitHub, and hopefully you learned something from this. In next tutorial, we're going to be improving our collision, making it to the right or left. We're going to be doing things like maybe make our UI components a bit useful. And yeah, you guys also can ask on Twitter or YouTube or on forums of Overlap2D whatever you want me to do in the next tutorial, and we'll do that together.